of today's of talks. So our next speaker is Marina Marinkovic from ETH Zurich, and she will be presenting machine learning phase transitions in a scalable manner on classical quantum processors. So Marina, please, the stage is yours.
Thank you very much, Andreas. Thanks to the organizers for the invitation. And I regret for not being able to be with you in Trento in person. It's great that you could organize some live discussions as well. But I'm happy to follow the workshop from Zurich and look forward to upcoming discussions. So we've heard already this morning that machine learning has been applied successfully in a number of test cases in lattice gauge theories. And I list here only a few applications that I've managed to catch so far and that will have been discussed in some talks. So one application is the phase separation that has been discussed in talk today, but there are many talks in this workshop which will discuss the applications of machine learning in learning the structure of phases of different theories. Then there were applications to generation of gauge configuration, and Ted will discuss, I assume, this also in the continuation of the workshop. Then there will be, in fact, a talk, I missed to add a point here, but there will be also a talk for applications to signal to noise ratio, as well as to the application of introducing this contour deformation to reduce the sign problem. In this talk, I will focus on the simplest method possible and one of the first applications of machine learning in order to learn the phases of matter, and this is the support vector machine, which belongs to the class of supervised learning methods, which are aimed at performing the classification of the input data. And there were, so the seminal application by Juan and collaborators already several years old, and then the following up applications have been mentioned of support vector machines in learning the phases and so the critical parameters and the classifying the phases of matter in simple condensed matter systems, such as the Ising model, XY model, and in this talk, I will also show some preliminary data for the POTS model. Then I apologize for this non-exhaustive list of other successful applications, and I point you to the very nice plenary talk in this year's Lattice conference by Sebastian, and as well as in the talks in this workshop. As already mentioned, so in our work, we apply a support vector machine in order to reproduce some of the data already obtained at the Ising model, as well as in the POTS model, and 5 to the 4th theory in 2D. And then when moving to higher dimensions, we noticed that much larger data sets will be needed in order to train our support vector machine. And we contemplated on 2 possible ways in which we could speed up our calculations with support vector machines with the aim to apply it in higher dimensional lattice gauge theories. So while the methods that we have discussed so far work very efficiently in 2 dimensions, we have seen that in higher dimensions we need to train for with larger data sets, and for that serial codes and also codes on our we assume that also codes on our classical computers might take longer than needed in order to perform, let's say, to generalize the procedure developed for condensed matter models to, let's say, the classification of phases in 4-dimensional QCD. And the first path that we followed in order to speed up the computations in high dimensions consists on using our classical computers, but instead of using the serial code, we wanted to speed up our application of Support Vector Machine by parallelizing the code. So there are already a number of publicly available tools which would allow us to perform the learning in parallel, but as for physics problem, custom-made solutions are the most efficient ones. So we embarked on constructing a parallel version of the Support Vector Machine that could be applied on large amounts of data needed for these high-dimensional theories. Then the second option, which I will briefly discuss towards the end of the talk, is an attempt to speed up the Support Vector Machine learning by replacing the classical kernel with a quantum kernel. So before moving on to the details of the parallel implementation of the Support Vector Machine, since this morning we mainly discussed neural networks, I will use this opportunity to remind you in a nutshell, what does the Support Vector Machine algorithm do? So if we want to perform some binary classification of the data in training, we can represent each data point as a d-dimensional vector, and then we can construct this d-1 dimensional hyperplane, which will separate the Euclidean distance between the hyperplane and the nearest training vectors. And these nearest training vectors, the closest ones to the hyperplane, are also called support vectors, therefore the name of the method. And this minimization procedure is, or actually maximization or minimization, depending how we define the problem, is the process that we are trying to implement now in an optimal way. So if we imagine once again that we have linearly separable data, and let's say that we denote the vectors with xj. I'm sorry, I'm hearing some background noise. Give me just 1 second. I will remove the noise. So, so if we have, so let's say our data set in case of gauge field theories, this xi, xj would be the our gauge configuration, and we can use the binary classifier to say whether it's on one or on the other side of the phase transition. So then we would minimize the minimize our W, which is defined here as subject to certain constraints, and this is equivalent to maximization problem if we introduce Lagrange multipliers appropriately, and then we need to maximize this maximization of this expression would correspond to the solution to this Lagrange multipliers, would give us, define us exactly this optimal hyperplane, which has the maximal Euclidean distance from the separable, from these two separable data sets. So in case that our data is not linearly separable, then we need to find a way to transform this nonlinear problem to a linear problem. And this often amounts to moving to higher dimensional space. So formally, this moving the problem from d dimensions, which is a small d, is our original problem, which is not linearly separable, to some high dimensional problem, which is this large d, is defined by a feature map. But in support vector machines, we actually, all we need is just a scalar product between these elements. So we do not actually need, we do not necessarily need the, to know exactly what is the feature map that we are using, as long as we define our kernels, which will give us the necessary scalar product needed for this in order to perform this previously introduced maximization. So if we know the kernel, this is sufficient in order to compute our function L, which we want to minimize, and then we obtain the values for the variables y, which can be either +1 or -1, and which tells us whether our corresponding data element of the data set belongs to one or to the other class. And we can apply this to any types of data, and among other things, one can apply this also to gauge configurations, or in case of condensed matter systems, those would be the spin configurations, spins up and down. The collection of a single configuration corresponds to one element of the data set. And it turns out, as demonstrated in the works listed above, that, for example, for the Ising model or other simple two-dimensional theories, as it was mentioned also already in the talks this morning, because this approach is not unique to support vector machines. One can also apply neural networks and train the algorithm away from the critical region, say for the two-dimensional Ising model at the temperatures far away from the phase transition, such as, let's say, in this example, 0.5 and 5 in the units, if we assume that the Boltzmann constant is equal to 1 and that this j is also equal to 1, then one, as we've seen also earlier today, one gets for two-dimensional Ising model a very precise estimate of the critical temperature, for example. And we can perform that also for three-state Potts model, but also for other choices of Q as well. And I demonstrate here, and I list here some examples of this classification performed by the using support vector machine for different choice of kernels, so linear and then polynomial kernels of higher dimension, as well as the Gaussian kernel, together with a sample choice of neural network as well, just to confirm the result. And the agreement between different methods is very good, and one gets the temperature of the phase transition very precisely also for these extended models. But this is all happening in 2 dimensions, and very few data, so the training data in 2 dimensions, once we train the training data, the data that we need in order to train the algorithm is quite extensive. But once we move to the test data at which we need in order to obtain these plots at each temperature in between these end regions, we can obtain very precise results with only a limited amount of data. So this n here equals to 5, 10, and 20. corresponds to the amount of test data that one needs at each particular temperature. And this the small amount of data in between the two training regions actually is something which makes this type of methods very promising for obtaining information about the critical temperature in the systems where we do not know what is the analytical solution yet. Now, if we want to move to higher dimensions, then we mentioned that we want to parallelize our approach. And this corresponds to, if you write the maximizing function, which we had previously, if you write it in a vector form, the classification corresponds to maximizing the function which has such a form where alpha is a vector constructed out of all of the Lagrange multipliers. And so this maximization procedure is subject to certain constraints. And I did not write here the KKT conditions for optimal alpha, but if one looks at these conditions, then we see that by optimizing this, the optimization of this function corresponds to getting the solution of alpha equals to, so the particular element of the vector of Lagrange multipliers for most training vectors will be equal to zero. In fact, only for support vectors, this will be equal to non-zero, or for some falsely classified data. And so this tells us that our solution of this optimization problem is a sparse vector. So the conjugate gradient algorithm can be used to solve this optimization problem instead of the usual sequential minimal optimization, which is commonly implemented. And once we have the conjugate gradient, then we know that there are many ways how to parallelize the conjugate gradient. So what I write here on the right-hand side is the algorithm for the serial method, which has been proposed already in the early 2000s by Venn and collaborators. And this algorithm proposes how to replace the sequential minimum optimization with conjugate gradient methods. Since, as we can see here, this problem is ideal. So the function that we are trying to maximize is ideal for optimizing the gradients. And once we have written down this algorithm, how to optimize, so how to form the classification by using the conjugate gradient instead of sequential minimal optimization, then we embarked on implementing this the conjugate gradient algorithm on which would work on multiple CPUs. And before implementing with the conjugate, you can't hear me anymore?
No,
can you hear me?
I was, because you have a question maybe which is related to what you just presented. I mean, maybe you want to have a look. I mean, Barak asked that question. I mean,
Awesome.
I'm sorry for interrupting, but maybe it's a good point to answer the question. I don't know.
Sure, no problem.
Yeah, sure. Sorry, I was actually asking about the previous slide. So it's kind of, and actually, sorry, one before that. So the slide about the, the phase transition itself. Yeah, so it's kind of a general question. I'm basically wondering, how do you choose the hyperparameters? So, presumably for some systems, not all choices will give you the same temperature. So how would you determine which one to use?
Yeah, that's a good point. So I mean, so that's why we started from some lower dimensional systems where the solution is known, but like in actually, the way we determine this, well, the error of the estimate with a particular methods is by looking at the standard deviation of the probabilities at each of in each of these values. So and of course the error is the largest at the probability 1/2, because because this is the region where both the critical region where both phases coexist, and this is where we also know that other methods have difficulty predicting as well. So I mean, I think that the knowledge of the system helps in the symmetries of the system as well, but and also, I mean, some of the things discussed in the previous talk by Sebastian, I think, were also are pointing us in the good direction. But I do not have a general answer to that. I think that.
Hi, Marina. Barak, it's Biagio here. Just wanted to say that in a paper that Marina quotes at the beginning, we studied that, and if you do not make choices that are actually, I mean, illogical, then the critical temperature is pretty stable, and you can verify that with the finite size scaling analysis, that they all converge to the expected result. We did that for the Ising model in particular.
I see. So essentially, you expect that all different choices will all converge to the same point, but with different finite size effect.
Yeah, exactly. It's like
different
observables.
Exactly. I understand. Okay. Thank you.
Thanks.
Yeah. So the paper that Biagio is referring to is this second one here. So you can look up in more detail in this archive reference. I think also what Sebastian told us this morning. So I mean, when Biagio says about if the choice is not completely illogical. So in that sense, like if your kernel is not such that you kill the relevant information in a sense, then one can expect. But now the estimate of the error then remains an interesting question, which I'm not going to go into much more details here.
Okay.
But
thank you.
Thank you for the question. So where was I? Yes, I said that so before implementing this conjugate gradient algorithm, we performed the optimization of the operator H itself, such that it's implemented in such a way that in both the memory usage and the time in the of the application is optimal, and then we divided the data set across multiple nodes and let the MPI handle these different data sets for each step in the conjugate gradient, as it's usually done in parallel applications of conjugate gradient algorithm. Then it turns out that instead of having two sides communication, implementing RMA, the one-sided communication was beneficial, and the typical data sets at which we obtain fairly good scaling are of the order of hundreds of thousands entries of the training data. I show here the part of the optimization related to one-sided communication. So if we didn't have one-sided communication, then the good chunk of execution time went into the MPI part of in the communications. But then with one-sided communications, then the actual application of the kernel was the dominating factor, as it should be the case. This profiling was done with a particular tool called Vampire, And this work was done together in collaboration with John Cormican, one of my students in the Trinity College Dublin. And these benchmarks that I'll show you here demonstrate that we got really good scaling up to 8 nodes. Our cluster had 8 CPUs per node, so in total up to 64 processors. We got not ideal, but very close to ideal scaling, which is not easy to achieve with the problems such as classification on this large amount of data. Now, the next step would be to move this also to try to use GPUs. So this is purely CPU parallelization that we performed here. And in this second part of the talk, I will now move to an alternative way to speed up this training with support vector machines, which will attempt to utilize the recent development in quantum computing. And so we know that if we have the feature space of the size n and the training the size of the training set, which is m, then our time needed for the execution of the support vector machine classification will be some polynomial of n and m. Now the question is whether this can be faster than this polynomial, arbitrary polynomial for a particular situation. And in some cases where one can actually achieve the speed up, the exponential speed up. So if one of the two, so if the training set is very large, as is the case usually in higher dimensions, then one obtains, instead of polynomial in m, logarithmic in m time, if one applies the quantum algorithm proposed by Rebbentrust and collaborators. Now, so this would be what's called quantum vector machines, quantum support vector machines algorithm in the literature. And what we have applied on the classification in the Ising model is the so-called quantum enhanced support vector machine. So in the first case, by Rebbentrust and all, they start from the classical vectors and immediately change into the quantum vectors before applying the kernel and performing the classification. While in this quantum enhanced support vector machine, only the kernel is computed as quantum, but in the remaining of the process, the classical support vector machine algorithm, which I listed previously, is followed. And this was proposed some 3 years ago. In early 2018 is when all of these papers appear on the archive. And it took a while until the community actually picked it up and applied it to some real test cases of data classification. So, so once again, this quantum enhanced support vector machine approach does not deal directly with quantum vectors, but it starts with classical data, then maps it to quantum states on which the kernel is applied. So the kernel is quantum, and usually consists of some applications of unitary operators on the quantum vectors, and then afterwards, since a result of this application is again a real number, then we can have it. In that way we obtain our classifier, which tells us whether the data is on one or the other side of the hyperplane. So, so this quantum enhanced support vector machine approach defines the kernel function as some scalar product of some feature. Of some quantum vectors in feature space, and then defines this feature map by unitary circuit family and arbitrary unitary circuit family. So this unitary can be constructed from different combinations of Pauli matrices. And this approach proposed in this paper by Halucha and collaborators. These are mainly members of IBM Q research team who designed this algorithm. And so basically, instead of having the classical kernel, one can implement an arbitrary quantum kernel. And the implementation of this approach already exists in a Qiskit, which is open source software written in Python, where one can construct their own circuits and implement different type of quantum algorithms and run them also on real machines with very few qubits for now. So if one registers for this IBM quantum experience, which is publicly available, then one can run on machines up to 5 qubits currently on publicly available machines, but in some private usage, they have up to 60 something qubits. And this Qiskit also has packages available for quantum machine learning, such as this approach that I mentioned previously, this support vector machine, where the kernel is constructed by application of different unitary operators to quantum vectors, which are constructed from our original classical vectors. And so there are different types of unitaries that one can apply here. So the few that we that are implemented in Qiskit directly and that we tried on our Ising model, that data are what's called the Z feature map and ZZ feature map. In one case, so we have in this previous formula here that we can have, if we have n qubits, then we have different combination of single qubit or 2 qubit or 2 gate applications. So in one case, if we have one, then we all, and if we apply, if our choice for the unitary is set gate, that then this is called the Z feature map. And then if we allow for the combination of 2 gates, then this Z feature map is applied, and we can also have an arbitrary expansion in Pauli matrices. But if we focus on a single qubit gates, then this would be this Pauli Z expansion. And here are the first results that we obtained on a 2-dimensional Ising model, a very small lattice, so 3 by 3 is our lattice here due to the amount of qubits that we had available in this on this free cluster, which was 5. And we applied the same procedure as described previously for the POTS model. So we train at 0.5 temperature and at 5 temperatures, and in between with the slightly larger steps, because it took a little bit longer to run all of this in this quantum computing queue. So we take slightly larger steps, 0.5 in temperature units, and for different choices of number of training samples for each temperature in between. So in the left we have 20, and in the right we have 80. We see that one can get well, good enough estimate for such a small system of the critical temperature in 2-dimensional models. Of course, this needs to be tested also at larger lattices, but what we focused on, so since we couldn't test the method in full size with finite size scaling and everything, because we couldn't run larger systems, we compared the classical learning and the quantum learning, the score, which tells us the quality of our classification procedure. So so once since we know what is the actual label of each of our elements of the data set, then we can compute how in which percentage did the algorithm correctly classify the particular configuration. And in case of the quantum, the three choices for the unitary for the quantum machine learning, we got a slightly better score than for the linear support vector machine. As far as the timing is concerned, we do not we couldn't measure whether this is more efficient in time. We suspect it is, but currently the machine gives out the time together with the wait time, and we're not able to actually extract the actual time of the execution of the on the classical computer on the quantum computer, but one only gets the queuing time plus the execution time, and the queuing time is currently quite long on these freely available IBM Q resources. All right, now I'll conclude here by saying that we need to make the execution of machine algorithms more efficient, and we started with the simplest possible method, which is the support vector machine, which we plan to also apply this to higher dimensional, to other methods as well, not only support vector machines. Then the motivation was to be able to perform phase classification in higher dimension theories, as in the two-dimensional theories we have seen that up to a few offered questions that we've discussed previously, that this method is quite successful. Now the development towards D dimensions is in progress, and one possible way of making this algorithms more efficient is to parallelize them. I've discussed a particular method to parallelization for support vector machines in general case. And we plan to speed up this parallel implementation by writing and optimizing GPU for GPUs, this parallel version of conjugate gradient. Thank you very much. Are there any questions?
Thanks a lot, Marina. So questions? Or maybe there are questions online. Let's check.
I saw one question in the chat, but that's the one which we discussed already, right?
This is a previous question. So yeah, actually, I have a question, and regarding the plots you showed. I mean, there you basically denote. Is it an error band? I mean, if it's an error band, how do you extract that?
Yeah, that's so. They said what we look into is the standard deviation of this probability for each particular temperature, and then assign the error bar as this width of the standard deviation.
Okay.
Whether there is a better method, that's something I'd be curious to hear about.
Okay, so I think there's still plenty of time. I think we still have like 10 minutes for the next talk. So I mean, if there are more questions, feel free to ask. In the meantime, maybe we can have a short break. So thanks, Marina.
Thank you.